So in this lesson, what we're going to do is dive right into Verilog. And the first thing we're going to do is implement a mux. So that's the example we're going to use. So what is a mux? A mux is a multiplexer. And let's just do a brief review of what a multiplexer is. So schematically, it's usually represented like this. A mux is usually represented with this shape. And we are going to draw a 2-bit mux. So a mux will usually have inputs x1 and x0. So this is a 2-bit mux. We'll always have a single output. And I have 2 bits for my input and then a third bit that operates as my selector. Okay, so how does this work? When the value of the selector is 0, the output y will be equal to whatever x0 is. And when the selector is 1, the value of y will be whatever x1 is. And the analogy I always give is of an HDMI switcher or splitter. So normally when you have these HDMI splitters, you can have multiple inputs, like let's say one from your game console and one from, I don't know, your Roku. And then you have an HDMI output going to your TV. And so depending on the value or the switch on the splitter, either you will be outputting to your TV the Roku signal or your game console signal. So this is very similar to the operation of a mux. In fact, you can think of an HDMI splitter as like a multiplexer, in fact. So let's do the truth table for it. So again, this is a 2-bit mux. And we have 3 inputs. And we have a single output. And given that we have 3 inputs, we know that we need to have 8 rows of the truth table to reflect all the possible permutations of our 3 binary inputs. Now, we know that, like we said, when s is equal to 0, in that case, y is going to be equal to x0. This is the operation of a mux, as we just said. And when s is equal to 1, the selector s, output y is going to be equal to x1. So all that means is that over here, when s is equal to 0, output y is going to be this value. And similarly, when s is equal to 1, output y is going to be this value, x1. And let's derive the Boolean expression for it using a K-map. And we've got 2 groupings like so. And our final Boolean expression looks like this. Which makes sense because, like we said, when s is equal to 0, the output y is going to be equal to x0, and when s is equal to 1, the output y is going to be equal to x1. And if we were going to draw this as a gate level schematic, it would look like this. So I would have S, and I would have this signal over here would be S bar, and I would have X0, And this expression over here would be S bar and X0. And then I would have X1 over here and S. And this expression would be S X1. And here I have an OR gate, and this output here is Y. So I can implement my multiplexer, my 2-to-1 multiplexer, fairly simply with just an inverter, 2 AND gates, and an OR gate. And that's what I'm going to do in Vivado 2020.1. And I'm going to create a new project. We're going to implement our MUX. And as you're going to see, as with almost everything to do with coding, there are always so many different ways to implement. And we are going to do a couple of those ways today. So for my project name, I'm just going to call it MUX221. And I will leave my project location as just the C drive, but of course you can change that. And I'll keep checked off the create project subdirectory. So that creates the whole project hierarchy. Now I'm going to keep checked. Do not specify sources at this time. I'm going to create and add my sources later. Click next. Oops, that's not what I wanted to do. I wanted to check off. For some reason, it still asked me. But anyway, I'm going to check off do not specify sources at this time. Now I get to select my part. We're going to target the basis 3, click next, and look this over. Everything looks good. I'm going to finish. So it's going to create my project now. All right, so first thing I want to do is add a new design source. And I can do that in one of multiple ways actually. I can click add sources over here. I can click this plus over here. I can right click on design sources and select add sources. And I believe I can also do it through the file menu here, add sources. So whichever way you choose, these methods are all equivalent. I'm going to go ahead and add a source. I am asked for 3 different types of sources I can create, but in this case, it's going to be a design source. So in other words, what is a design source? It is Verilog code that specifies the functionality of my design, and that's what I'm going to do. And the functionality that I want to specify is the functionality of a 2-to-1 MUX. So I'm going to create a new file in this instance. And the file type, so you'll note that there are multiple file types. So they can be in Verilog, a Verilog header, system Verilog, or VHDL, which is another hardware definition language, or memory file. But I'm going to just stick to Verilog. And my file name, I am going to stick to MUX221 and leave the file location as local to project. So it will place it inside the project hierarchy. I'll go ahead and click OK and finish. And now I'm presented with this define module window. And what does that mean? So a module is equivalent to a gate or an IC that you would place on your breadboard, except in this case, I get to define its functionality. And instead of my IC having a name like, I don't know, the 74LS00 or something like that, it will have, my module will have a friendly name that I will give to it called MUX221. And instead of having pins, so maybe I have 3 input pins and 1 output pin for a MUX. In this case, I have ports, and my ports have friendly names. So they're not numbered, but they have friendly human readable names. So I'm going to go ahead and recall that my MUX had 3 inputs and 1 output. So my 3 inputs were composed of selector S, and that was an input. And then I had X0, which was also an input, X1, which was my third and final input, and then I had Y, which is an output. And we have not talked about what this does, but we will later. So I'm going to go ahead and click OK. This is all I want. And as you can see, Vivado is going to create this new file for me and place it under design sources. And I'm going to double click on it. Notice that it went bold, and we're going to talk about the significance of that later. Okay, so let's just take a look at the structure of this file that Vivado created for me. So the first thing is that I've got this backtick over here with what's called a timescale directive, and that's used in simulation. So that's out of the scope of what we're doing now. So let's just ignore that. The next thing I have is a whole bunch of these forward slashes. And for anybody who's ever programmed in C or Java or equivalent language, you will know that a forward slash denotes, or two forward slashes rather, denote a comment. So in other words, it means that anything that follows two forward slashes on a line will not be interpreted as Verilog code, but it will just be considered a comment. So I'm going to go ahead and minimize them. But while I'm here, I do want to talk about the importance of commenting your code. And there are really three main reasons that you want to comment your code. And you want to comment often, be extremely verbose. And I'm going to give you a few reasons, like I said. So one reason is before you settle in to write, so in this case, we have a pretty simple module that we're implementing, 2-to-1 mux. But if I had something a lot more complex, I maybe don't know exactly how I'm going to implement it, but I just kind of want to guide myself. I'm going to write these comments in my case, English, but in your case, it might be another language. So I'm going to write these comments to myself that sort of allow me to conceptually zoom out on the functionality of what I want to implement, and then worry about the details of it a little bit later. So I will translate my English words into Verilog code at some point later. But it allows me, having these comments allows me to sort of map out the structure and functionality of my module. And the second reason that I want to put comments, and I want to comment liberally, like I said, is because you'll be surprised how much future you is not going to remember what it was that past you was trying to implement. So when you come back to your code in like 2 or 3 months or a year or whatever it is, you will have completely forgotten what you were trying to do and how you implemented it. And this will provide a guide for future you. And the third thing is that when you're working on group projects or team projects, it's not necessarily future you who's going to come in and look at your code, but maybe somebody else that you're collaborating with, a colleague. And maybe you'll have left the company by then, or you'll be on another team, or whatever it is, you're somebody that you're working closely with. But they are going to need to modify your code, maybe because they're debugging or they're troubleshooting, or they're trying to add functionality. And the comments will be much more readable for them than Verilog code. So for all those reasons, commenting your code liberally is extremely important. Okay, so now let's look at the structure of a module. So what did Vivado do with that information that I input into the create module window that we had earlier? So for one thing, I have this keyword module, and then I have the name of the module that I gave to Vivado in that window. I called it Mux 2-to-1. And then inside these parentheses, opening and ending parentheses, I have a comma separated list of my port names and the keywords input or output beside them. So again, my ports can be either inputs or outputs, and I need to specify it. This is a comma separated list. And finally, I have this semicolon which terminates my statement in Verilog. So all Verilog statements have to be terminated with a semicolon. And more on that later. And then finally, I have this end module keyword, and the functionality for my module goes in between the module definition up here and the end module keyword down here. Now, a final comment that I want to make on this is that there are constraints to how I can name my modules and my input and output signals, and as you will see, other signals that we will be able to define in Verilog that are not inputs or outputs. So in this case, if I wanted to name my module instead of mux 2 to 1, if I wanted to call it 2 to 1 mux, Verilog or Vivado in this case is not going to like that, and it's going to give me this sort of, it's going to underline it with this red wavy line, similar to like when you have a spelling error in Microsoft Word, and it's going to tell me syntax error near 2. And basically what that is telling me is I do not like it when you start a module with a letter instead, with a number instead of a letter. So although there are exceptions to this, where you can start with you can start a module name with other characters that are not lettered for our purposes for this course, pretty much everything we do will need to start with a letter. You absolutely cannot start it with a number though. Similarly down here, if I wanted to start my input x0, if instead of calling it x0 for some reason I want to call it 0x, well, again, I'm going to get that red wavy line that indicates to me a syntax error. In other words, a problem with my code. So you can think of syntax as kind of like the grammar of my code. Now, while English or whatever your native language is, any human languages are fairly forgiving about grammar. You can still convey meaning even with slightly incorrect grammar. Computers are not forgiving, so you have to be very precise about your syntax, about how you specify things in Verilog, and in fact in any language. So let's go ahead and create the functionality or specify the functionality for our module. And there, as with everything, there are always so many ways to do it. So we are going to start with multiple ways. And the first way that we're going to start is what's called gate level. Okay, so I am going to make a comment here, and I'm going to write down our Boolean expression. So recall that this is the functionality that I want to implement, that y is going to be equal to s bar x0 or s x1. And there are so many ways to do this in Verilog. So I'm going to show you first one gate level way. What I'm going to do is I am going to define some interim signals. So going back to our schematic, I'm going to define some interim signals that are the outputs of my inverter and my two AND gates respectively. So the way I do that is with the wire keyword. And I'm going to define a comma separated list of signals. I'm just going to give them random names or sort of human readable names, but I define them. I, as the designer, define the names of these signals. And they're going to be comma separated, and then I'm going to terminate the statement, as always, with a semicolon. So I'm going to call these signals S1, SX0, and SX1 respectively. And then don't forget, I terminate that statement with a semicolon. And now what I'm going to do is, the first thing I'm going to do is I'm going to define my signal S bar. So to do that, I have these built-in gates in Verilog. So I have very low-level gates like not, or and, or. Those are all built into Verilog. So I can do them like this, and the way that I define an AND gate is like this. I write the keyword and then, as always, I open and close my parentheses. I'm going to terminate with a semicolon, but I'm going to add my signals in here. So, and actually, I did say I started with N, but in fact, this should be a not. So I'm going to just comment this for now. We'll come back here. And I'm going to, so what we said is we were going to define not S. I actually don't like this name S1. It's not clear that it's inverted S. So I'm going to terminate with an underscore, which is an allowed character. So I'm going to call my inverted S signal, I'm going to call it S underscore. So again, underscore is an allowed character inside the name of my wire. So how I do this, again, so same way, I'm just going to write out sort of the skeleton of my NOT gate. So you can think of it if you've ever programmed in a high-level programming language, again, like C, you can think of gates like this, and the parentheses, you can think of them as calling functions. However, I'm getting this error message, and it says that I need at least one output and one input into this gate. So the way that I define my S bar signal is I put the output first, and then I put the input S, and the effect of this statement is going to be that it's going to create the NOT gate, an inverter, where the input is S and the output is S bar. So the outputs always come first in these built-in gate definitions. So the second thing I'm going to do, so I have now just assigned to my internal signal S bar, I have assigned to it the output of inverting S. And now I'm going to do the same with my AND. So I'll reuse this code here. So again, outputs come first. So the output of my AND gate is going to be this wire over here. So this is going to be my first AND gate, and the output is going to be SX0. And I have two inputs. So it doesn't matter in which order I specify the inputs, but my outputs always have to come first, so immediately after the opening parenthesis. So my two inputs to this AND gate are S bar, which I defined just here above, and X0, which is my input. And then similarly, I need a second AND gate. My second AND gate has as output this signal that I called SX1. And it is going to have two inputs. The first is my top level input S and my top level input X1. And then finally, I have an OR gate. The output of my OR gate is simply my output Y. And the inputs to my OR gate are these two signals, SX0 and SX1. And again, I close my parentheses, and until I add my terminating semicolon, I will have that red wavy line underneath the keyword and module. Okay, so what did I do here? So the first thing that I did was I declared all my wires, all my internal wires that I needed. So this is similar to like on a breadboard, if I took a red wire and I made the red wire the output of my inverter, where the input was my signal S. And I had, let's say, a blue wire, which would be the output of an AND gate that had S and X0 as inputs, and had similarly a third wire called SX1 that was the output of my second AND gate. And in Verilog, I can give these wires human-friendly names, again, just like I gave to my input and output ports. And really what I'm doing is I'm just translating my schematic that I did earlier. I'm translating that into Verilog code. So I have, just as in my schematic, I had one NOT gate or one inverter, I had two AND gates and one OR gate. That's exactly what I have here. So I'm going to go ahead and save that schematic for the RTL analysis over here. So I'm going to click on it and let's see what it generates. So as we can see here, the schematic very closely resembles what we had drawn earlier. And the only difference is that the inverter has been replaced with this inverted input into the first AND gate. And I can tell it's an inverted input because of this bubble over here. The constraints file for the basis 3, and you're going to see why the constraints file is board specific in a second when I add it. So again, I'm going to add a file using this here plus button. I am going to add or create constraints, and in this case actually I'm going to add the file. I've put it here on my desktop. And it's the basis3 underscore master dot xdc. And if you look over here on the right, you will see that all the lines are commented. Now, the comment character in a constraints file is the hashtag or pound symbol, as opposed to in a Verilog file where it is // So every line in this constraints file is commented, and it's on us to uncomment the lines corresponding to the pins that we need to use. So the purpose of a constraints file, now let's add it, and I've copied it into the project, and here I'm going to expand the constraints file. And I'm going to double click on basis3 underscore master dot xdc. And as you can see, this lists every pin on the basis board that actually correspond to pins on the chip itself. And if you look carefully actually at your basis board, you are going to note that next to, let's say, the switches or the LEDs or the push buttons, you actually have the pin numbers on them. So you can actually see the pin numbers just by looking at the basis board. And this allows us basically to map inside our mux. So again, we have three inputs, S, X0, and X1, and we have an output Y. And let's say we want to map them to maybe switches. So our three inputs will map to three different switches, and our output will map to an LED. So let's actually just scroll through this constraints file and get a little bit familiar with it. So over here, we have all the switches, and over here we have all the LEDs, and then there's the 7-segment display, the decimal point for the 7-segment display, and these are the anodes. So these allow us to enable or disable specific 7-segment displays. There are 4 on the basis board, and we can enable and disable them individually. Here we have the 5 push buttons on the basis board, and here we have our PMODs. So if you remember, we have PMODs JA, JB, JC, and JX ADC. And each of those PMOD ports have 12 connectors, and 4 of those connectors are either VCC or ground, but the remaining 8 we can map as input or output. They're I/O. And those are listed over here. We also have a VGA connector and USB RS-232 interface and the human interface device. Here is the quad SPI flash. We're probably not going to use any of those last three, but we will use all the others eventually. So let's start over here with switches. Okay, how does this work? Now, what I want to do is map the pin number, so the package pin number. So for example, switch 0 is V17, and I want to map it to a port name. That's this get ports thing over here. And I need to do that over two different lines. So if I want to uncomment, let's say I need to uncomment 3 different switches. So these 6 lines correspond respectively to switches 0, 1, and 2. And I'm going to go ahead and uncomment them. And an easy shortcut actually to comment or uncomment a line is select the line and then press Control/, which actually did not work in this case here. Here we go, Control/. So now, this is not going to work as is. Why? Because right over here what this line does, or these 2 lines do, is they're mapping pin V17, which is actually switch 0 on your basis board, to a port in my Verilog file called switch 0. And you're going to see that these square brackets over here, they correspond to buses or multi-bit signals, and we don't have that we haven't covered that yet, and we don't have that in our MUX design. What we do have are inputs X0 and X1. So what I'm going to do over here is I need to make sure that my basis 3 constraints file corresponds to the port names that I have defined in my Verilog file. So I am going to go ahead and map, so this line maps the port signal S that I defined as an input in my 2-to-1 MUX. And over here I set it as CMOS 3.3 volts. So instead of switch 0 over here, I am going to call it signal S and switch 1. So again, I'm replacing everything inside of the curly braces. So instead of switch 1, I have actually called it I've called this signal X0 inside my MUX 2-to-1 file, Verilog file. So I'm going to replace it here, X0. This is going to be switch 2 is going to correspond to X1. So basically, what am I doing here? I am telling Vivado that on the basis 3, the pins V17, V16, and W16, which actually correspond on the board to switches 0, 1, and 2, correspond in my Verilog file to port signals S, X0, and X1. That's what this says over here. Now I'm going to scroll down to the LEDs, and I'm going to do the same for LED 0. So what I want to do is I'm going to uncomment these 2 lines. And again, I can do that with Control/, and I'm going to replace this line LED 0 simply with Y, because that's the name in the signal as I have defined it in the MUX 2-to-1 file. So we're going to learn a better way of doing this, but not yet. So this is how we're going to do it for now. So remember that the way this works is a beginning square bracket has to have an ending square bracket, and a beginning curly brace has to have an ending curly brace. So just make sure that you have the beginning and ending curly brace here, and you don't delete. And you don't delete anything else. You don't delete the ending curly brace, for example. So just want to make sure that you do it properly. Okay, so I'm going to go ahead and generate the bit stream. And that is going to launch the synthesis and the implementation. So these are two stages that I need to go through in order to generate the bit stream. And once that's done, I'm going to go ahead and program my basis board. So you can do it from within Vivado, but since I am running Vivado remotely, I am going to transfer the bit file and upload it to my machine. Okay, so let's test it out. So notice here, I've programmed my basis board, and I can tell because the done LED over here is lit. All right, how does it work? So I've got, let me move all the switches down. And this switch over here, switch 0, is the selector. So right now the selector is at 0, which means that whatever the value of X0 is, that's this switch right here, will appear at the output LED over here. So to test that out, I am going to move switch 1, which corresponds to X0. I'm going to make it high, and now my output LED should be high, and it is. Okay, how about if I move the selector now to the 1 position? And that means it's going to take the output from this switch over here, which is X1. So this switch is mapped to X1. Now I'm going to move the switch high, and the LED is lit. I'm going to move it low, and it turns off.